Welcome to physics class on web optics part 1. In this web optics, I will try to cover the following topics that are shown in the screen. The first one is electromagnetic waves, then wavefront, Hudson's principles, reflection of light based on Hudson's principle, refraction of light based on Hudson's principle, behavior of wavefront in a mirror, lens, and prism, then coherent sources, interference, Young's double slit experiment, and lastly we will deal with color in thin films. Now let's see the first one, that is electromagnetic waves. We know that in electromagnetic waves the electric field vector and the magnetic field vector vary sinusoidally and perpendicular to each other, and perpendicular to them electromagnetic waves propagates. Now for example, if your electric field vector is denoted by these red waves, okay, and it is lying on the plane of XY plane, and that of the magnetic field is varying sinusoidally, and it is shown here with a blue wave here, which is lying on the XZ plane, and perpendicular to both this electric field and magnetic field the electromagnetic wave will be propagating along x-axis. So what happened? Light is also electromagnetic waves, and these electromagnetic waves, okay, it is due to the electric field vector and the magnetic field vector, which are varying sinusoidally and perpendicular to each other. Now the speed of these electromagnetic waves depends entirely on the electric and magnetic field properties of the medium in which the wave travel, and not on the amplitude of their variation. Now we know that your speed of light in vacuum, it is expressed as 1 by root over of mu naught and epsilon naught, where mu naught is the permeability of the vacuum or free space, or epsilon naught is the permeability of that free space or vacuum. Now we know that these electric field and magnetic field vectors, as they vary sinusoidally, what happened perpendicular to it electromagnetic waves will be propagating, and these what the significance of this electric field is much there in the optics. Why? Because the vibration or the optical property of the electromagnetic wave, or rather the light wave, it is due to the electric field vectors and not due to the magnetic field vectors. Okay, when light travels from one point to the other point, say along x-axis, then this possible vibration of electric field will be all there in all the possible angles. That means perpendicular to this propagation, that means along x-axis, what happened, the electric field will be vibrating in all possible planes. So we call it that as unpolarized light. When this vibration, electric field vector vibration, if it is allowed to restrict to vibrate in a particular plane, then we call it that light wave. After restricting the plane of vibration of this electric field vector, then we will call it them as polarized light waves. Now let's see wavefront. Now a wavelet is the point of disturbance due to the propagation of light. Wavelet means small wave, okay, wavelet. So this is a point of disturbance due to the propagation of light. But first let's try to learn about what is wavefront. A wavefront is a locus of points having the same phase of oscillation. Now what is meant by this locus? Locus is nothing but this is a line or a plane or a surface formed by points, okay, which satisfy some mathematical condition or mathematical relation or mathematical equation. So those surface or those line or those plane formed by points by joining those points having same mathematical conditions or equation, or satisfying some mathematical condition or equation. We call it that as locus. In a circle also, now let's take it for time being as a circle like this, the outermost circle. How do we define circle? Circle is a line or a curved line, you can say, formed by joining the points having what equidistance from a fixed point. Suppose if this is the center of the circle of this outermost circle, then what happen, this circle is formed by joining those points which are equidistant from this fixed point, what we call as center of the circle. So from this center of the circle, all points which are equidistant from this fixed point, if you join it all those points, then it will be what, a circle. So that equidistance from a fixed point, that is the mathematical conditions. So those what surface or those line or those curved line or plane, whatever it is, formed by joining those points having some mathematical which satisfies some mathematical equation or condition, we call it that as locus. Likewise, for wavefront also, it need to satisfy some mathematical condition. What is that mathematical condition? That mathematical condition is nothing but that is having the same phase of vibration. So if you join all those points having the same phase of vibration or oscillation, then that point at that particular time we will call it that as wavefront. Now let's see this. Suppose if you are having a light source here, okay, point light source. A point light source means it is small as a point, or rather you can take it as a spherical source of light. Okay, small spherical source of light that can be considered as a point source. So from this point source, what happen at a particular time t, at a particular time t, if that oscillation, okay, starting from this source, and if it reaches at this particular time, say suppose small t, then what happen at this small time t, what happen, as this is a vacuum, let's take it that the vacuum, the speed of light, it is denoted by ct, by c. So what happen, distance travel, we know that it is equal to what, velocity into time. So your distance travel by the light waves from this source up to reach this particular point, that will be equal to ct. So this much distance will be traveled in all the directions. It will be reaching here, here also it will take this much distance, rather you can take it this as a sphere. Okay, this is not a circle, rather this is a sphere. In all directions light is propagating. So what happened at a particular instance, a small t, the first wave that we considered, that will be known as what, wavefront, whereby all these points on this wavefront what should oscillate or vibrate in the same phase. So if you join it all those points at a particular time having the same phase of oscillations, then this will be called as what, primary wavefront. Primary means at the first instant. Okay. Now if you consider somewhere here at this time, then what happened, this will be the primary wavefront. Okay, so there are many wavefront that I have drawn here, and I'm just taken out the outermost one, for example, okay, as an example. Now a line perpendicular to the wavefront is called a ray, and it will be always, okay, perpendicular to the wavefront. This light ray will be always perpendicular to the wavefront. Now if you take it somewhere here as the point, and if you take it, if you draw a tangent here onto this spherical surface, then what happened, the radial segment, we know that the radial segment is always perpendicular to the tangent, right? So what happened, this ray will be perpendicular to this what, spherical surface, rather the wavefront. So your wavefront and the ray will be always perpendicular to each other. So these are all the rays that is shown with a red line with an arrowhead. Okay, now what happened, this is about the spherical wavefront. Now let's see about the cylindrical wavefront. Now in the case of spherical wavefront, the source was also spherical in shape, or you can say point source. But in the case of cylindrical wavefront like this, these are all the blue colors are all that of the cylindrical wavefront. Okay, here I have drawn here two cylindrical wavefronts. Rather, I'm sorry, it is three. Okay, there are three. So one wavefront here, the cylindrical, another here, okay, and the last one, the outermost cylinder, it is the cylindrical wavefront. Now for such cylindrical wavefront, we need to take it a linear source like that of your tube light. Okay, linear means what? It is longitudinal, more in length than that of its diameter. Okay, so what happened, this cylindrical shape source, or you can say linear source, from this linear source all light waves will be emitting out in all directions, okay, from every point of each source. So I have taken only three here. So what happened, at a particular time, what happened, the distance moved by the light wave from the source, okay, that will remain same as it is shown here. I said ct like that. Okay, at that time ct, I will also draw only, I will take it the outermost cylindrical wavefront. So what happened, from this source, that means your linear source is somewhere here, okay, at its axis. So what happened, at any time say small t, what happened, the light, okay, from its source, from the linear source to reach here, it will take what, the distance will be what, during this time small t, the distance will be ct. So the radius, it seems that the radius is having ct for this cylindrical surface. So what, to reach these points, or this point somewhere here, here from the source, okay, it will take what, during this time small t, the distance will be this much ct. Why? Because your distance is equal to what, velocity into time. So what happened, at the same time, okay, the phase of vibration, okay, the phase of vibration or the phase of oscillations of this light wave will be having what, same phase, okay, all those points. So when you join all those points, okay, it will be having that of what, spherical, not spherical, rather the cylindrical shape. Okay, so these what, surface which formed by joining all those points having same phase of vibration or oscillation, we call it as cylindrical wavefront. As if you have considered these as for the first instant, then this cylindrical wavefront will be called as what, primary wavefront. At a later stage, what happened, we will call it that as secondary wavefront. Okay, so this primary wavefront is what, cylindrical in nature, so we call it this cylindrical wavefront as cylindrical wavefront, right? This wavefront as cylindrical wavefront. But what about this plane wavefront? What will be the nature or the shape of the source of light? But this plane wavefront, we can't have that plane source of wave. Rather, for the cylindrical, okay, for the cylindrical wavefront, we have what, linear source. For the spherical wavefront, we have what, point source or spherical source. Now if your point of observation is very far away from either from the spherical source or point source, or from the linear source, if the point of observation is very far away, and if you take it a small portion, okay, if you take it a small portion, if I zoom it like this, and if you take it a small portion here, small portion like this here, then what happen, it will be almost plane. If you take a small portion onto this cylindrical surface also, it will be almost flat. If this radius is very far away, okay, if you take it far away somewhere here, the cylindrical surface will be almost a plane like this. Got it? And some for this spherical source also, if you take it very far away from the point of source, from the point source or the spherical source, then that small surface will be almost plane like this. Got it? So what happened, for the plane wavefront, we don't require that plane source. Rather, it may be of any source, whether it may be what, point source or cylindrical. or linear source, I mean, what happened, the plane source, the plane wavefront will be there if the point of observation where you are considering that what wavefront, if it is very far away from the point source or from the linear source, then you can take it that as a plane wavefront. Now here also your plane wavefront, here it is what, perpendicular to the rays that are coming out. Okay, so it will be always perpendicular to what, the wavefront. Okay, with what, with those rays. Okay, now let's see about the Hudson's principle. What is this Hudson's principle? Hudson's principle is nothing but it gives the ways and means to construct the secondary wavefront. Okay, what is this secondary wavefront? Let's discuss it. We were talking about that of primary wavefront, right? Now you take it a point source at this S. Okay, at the point S here, you take it a point source, and at a particular instant of time, say let's take it as small t. At a particular instant of time, let's take it as small t. At this time t, what happened, the distance moved by the wave, okay, by the light wave, will be what, ct, right? So these points somewhere here shown with the red line, okay, these are all the points, okay, of the light wave at this time t. It will reach from this source up to here at the same time. That means during this time small t, at any instant, okay, of time small t, what happened, the light wave will reach simultaneously at these points. Okay, and so what happened, as it is vibrating with the same phase, what happened, this surface, I should say, this is not actually a line. In a two-dimensional way it will be just like a line, but if you think of that space, three-dimensional nature, then this will be spherical in shape. Okay, so this spherical surface, I will say xy, this will be what, the primary wavefront. Why primary wavefront? Because this is for the first time that we considered at this instant t, and these are also vibrating at the same phase. Okay, all points here will be vibrating in the same phase, so we will call it this as primary wavefront. Okay, and what does this Hudson's principle states? Hudson's principle states that each point on a wavefront act as a fresh source of disturbance of light. That means this wavefront, at every point of this wavefront, what we call as primary wavefront, will be considered as a fresh source of light. All those points will be acting just like the parent source. Okay, and it will be having that disturbance of light. Disturbance of light means it will be emitting out that disturbance, means wave. Okay, this will be distributing the light waves in all directions. That is the first principle. Now the second principle is what? The new wavefront at any time later is obtained by taking the forward envelope of all the secondary wavelets at that time. That means what? You take it at some later time. This was the first instant. Now let's take it at some later instant of time. That means after a time of dt from this t, that means the time will be what? T plus dt, right? At this time, what happened? As this, all the points onto this primary wavefront, it will act just like a fresh source, okay, of light, and it has a source of disturbance. That means light wave will be all emitted in all directions. So what happened, this, as this is a spherical surface, so what happened, there will be a spherical what nature of this source of light, and it will be emitting out, okay, light in all directions. So what happened at the time t dt, what happened, the distance moved by the light waves from these wavelets, what happened, it will be equal to c dt. This radius will be c dt, c dt, c dt, like this. All it will be emitting out in all directions. Got it? So what happened, if you join all those points having the same phase of disturbance at this time t plus dt, then it will be having a curve like this. What is this curve? This curve is formed by joining all those points having same phase of vibration at what time? At t plus dt. Then this will be also again another wavefront. X1, Y1 will be also a wavefront. And what type of wavefront is this? This wavefront will be called as secondary wavefront. Due to what? Due to the secondary wavelets. Wavelets means the small wave that is distributed by these points on the primary wavefront. Okay, we call it that as wavelets. So these secondary wavelets, I can call it as secondary wavelets. So these secondary wavelets, if it is emitting out in all directions, and if you try to join all those points having the same phase of vibration or oscillation, then this will be called as secondary wavefront. Why? Because this is at the later instant of time from this t. Okay, that means after the later time dt. So at a time t plus dt, we call it that wavefront. At some later time, we call it as secondary wavefront. So this secondary wavefront, it will be only in the forward direction. Why not in the backward direction? Because due to the Stokes law, okay, Stokes law, S-T-O-K-E. Due to the Stokes law, what happened? The forward direction will only be existed, and the backward direction will not be existed. Why? Because the Stokes law says that the intensity of of light, we know that intensity of light is directly proportional to the square of the amplitude. Okay, intensity I is directly proportional to the square of the amplitude. Let me write in short like this: amplitude square. Got it? So as intensity is directly proportional to amplitude square, but due to the Stokes law, this amplitude, okay, of the secondary wavelet is proportional to half times 1 plus cosine of theta. What is this theta? Theta is nothing but, it is also given here, 1 plus cosine of theta. What is this theta? Theta is the angle between the original direction of the incident ray and the backward direction. Okay, the backward direction of the wave means at any point. That means the angle between them is what? 180 degree. So 180 degree, so theta being 180 degree, what happened? 180 degree, the value of cosine of 180 degree is -1. So 1 plus of -1 means 1 minus 1. 1 minus 1 means 0. So your amplitude will be 0 for all those of the backward wavefronts. Okay, so if your amplitude is 0, there will not be no intensity. If intensity is equal to 0, it means what? There is no light in the backward directions. Okay, so what happened? Your forward wavefront will only be existed, and there will not be any backward wavefront. Got it? Yes, due to that, what happened? It will be having only the forward wavefront only. So your primary wavefront, then secondary wavefront. So your secondary forward wavefront will only be existed, and there will not be no backward secondary wavefront. Okay, if you are asked why there is no backward secondary wavefront, then you have to say that it is as per the Stokes law that amplitude of the secondary wavelet is proportional to what? Half times of 1 plus cosine theta. And for that of the backward wavelets, what happened? Theta is equal to 180 degree, and so what happened? 1 plus cosine of theta is what? 0. Now let's try to prove the laws of reflection at a plane surface on Hudson's principles. Okay, that means according to Hudson's principle. Now this xy is the reflecting surface. Okay, xy is a reflecting surface, and parallel ray of light is incident on it. when we say ray, don't confuse that. This is in the form of wave and it is coming in this. So the part of that light wave, if it is drawn with a line, then we call it that as ray. Okay, so parallel ray of light is incident on it. And what happened, the velocity of light, we know that in air it is denoted by c, right? So this is the point of incidence, a is the point of incidence, and onto this reflecting surface normal to this point of incidence will be denoted by n. And let's take it another point also of point of incidence c, and the normal at the point of incidence is denoted by n. Now let's take it that AB is the plane incident wavefront. Okay, plane incident wavefront. Let me zoom in. Okay, plane incident wavefront like this. So what happened, this AB, okay, AB is the plane incident wavefront, and if these blue lines are the rays, then what happened, we know that wavefront and the ray are always perpendicular. Okay, that is drawn here. Okay, so what happened, this angle of incidence, the angle between the incident ray and the normal at the point of incidence, we call it as angle of incidence. Then this angle will be also angle of incidence. It will be equal to angle of incidence, I mean. Why? Because this angle between B, A, N, let's take it as angle 1. Okay, for the time being, let's mark it this as angle 1. Angle what? B, A, N. So let's mark it this angle as angle 1. This as angle 1 like this. Okay, as angle 1. So what happened, this angle 1 plus I, this will be also 90 degree. Why? Because we know that wavefront and the ray are perpendicular to each other. So 1 plus what, I, will be also 90 degree. 1 plus I, this will be also 90 degree. And here also see your 1 plus this remaining angle BAC. Okay, 1 plus angle BAC, this will be also 90 degree. So what happened, if you cancel this 1, then your angle of incidence will be equal to what, the angle BAC. So that's why I mark it here as BAC. Got it? Yes. Similarly like that for this also, R plus, if you mark it this as D, C, and if you mark it this angle as 2, then 2 plus R will be also 90 degree. Here also 2 plus the remaining angle will be also 90 degree. Got it? This is 90 degree being normal, and this will be the plane reflected wavefront, and this will be the ray. So wavefront and the ray, they are perpendicular to each other. Similar to this, you can make it this also as angle of reflection. Okay, now what happened, in order to prove these laws of reflection, okay, angle of incidence is equal to angle of what, reflection. Then we need to take it the time. Okay, time for what, to reach by the light wave from this point B, okay, to C. During that time, what happened, from any point onto this wavefront, let's take it as A, should reach the point D onto the reflected wavefront. That means during the time, okay, when this point B reaches to C, at that same time, what happened, A should reach this point D. Then what happened, this CD will be what, known as the reflected plane wavefront. Got it? To do that, let's take it that any arbitrary point onto this incident wavefront, let's take it as a point E. Okay, during that time when B reaches C and A reaches to D, okay, from any point onto the incident wavefront, it should also reach the point G here. Okay, then what happened, we will confirm that this CD is the reflected plane wavefront. Now to do that, what happened, let's take it like this, EF. Okay, we know that time is equal to what, distance divided by speed. As I said, distance S is equal to what, the velocity into time. So your time will be what? Distance divided by speed, right? If you transfer it, then we can express time as distance by speed. Now this distance, as the light moved from E to F, the distance is EF, and the velocity is what? Velocity of light in the air medium is what? Denoted by c. So EF by c will be the time taken by the light, okay, wave to reach from E to F. Okay, I'm sorry, this is not for the refraction. I should take it for that of reflection, right? I think I have changed to the new slide, or this is here. So from E to F, okay, to reach from E to F, what happened? The time will be what? Distance divided by its speed. Now to reach from here F to G also, what happened? The time taken will be what? Distance Fg divided by c, right? So this, the sum of the time taken by the light waves from E to F plus from F to G will be the time taken by the light wave from B to reach up to C. Got it? That time is denoted by small t. So if this time taken by the light wave to reach from B to C, if it is having with the same time from E to reach this G through this F, then we can certainly prove that what happened? Your angle of incidence is equal to angle of reflection. But how? Let's see. So your EF from this right triangle, okay, from this right triangle AEF, okay, your sine of angle of incidence I will be equal to what? Perpendicular. Perpendicular is EF, hypotenuse is what? AF, right? So your EF can be expressed as what? AF sine I. It is done here, okay, by using that formula. As I have said, sine of angle of incidence is equal to what? EF by AF. So by using that, EF can be expressed as AF sine I. Likewise, your FG can be also expressed as FC sine of the angle of reflection, okay. And now this FC, here in this FC, we can express this FC in terms of AC and AF. We know that your AC in this diagram, your AC is nothing but it will be equal to FC plus AF, right? FC plus AF. So your FC can be expressed as what? AC minus AF, right? AC minus AF. Got it? So if you express it, this FC by using this FC is equal to AC minus AF, and if you rearrange it to associate AF here and another AF here, then you can take it common, okay. Instead of FC, if you put it this as FC equal to this, then you can associate this AF here and AF here, I mean, okay. And if you rearrange it, then it will be like this. Got it? It will be as it is here. Now let's see, this part is very important, okay. There are many methods to do it, but this one is much more simpler to you. And if it is asked to prove these laws of reflection by using your Hudson's principle, it will give you only 2 or 3 marks. It will be asked for 2 or 3 marks, and if it is for 2 or 3 marks, then this is more than enough, okay. So for rays of light from different points on the incident wavefront, okay, the values of AF are different. Suppose if you take it a point E, arbitrary point E somewhere here, then F will be somewhere here. So your AF, okay, this should not the time taken by the light to reach from any point onto this AB, that means incident wavefront, to reach this reflected wavefront, what happened? Your time taken should be independent of this AF. That is a meaning, okay. If you are taking this point E somewhere, F will be here, that means AF will be longer. If you consider E somewhere here, then F will be somewhere here, so AF will be shorter, right? So it should not be depend on this AF. But let's see, it will have different values of AF, but light from different points on the incident wavefront should take the same time to reach the corresponding point on the reflected wavefront. Got it? So T should not depend on this AF. So your T should not depend on this AF. If it should not depend on this AF, that means while writing the expression for these, okay, AF should not be there. That is the meaning. Okay, if this should not be there, that means what? AF is there, no doubt. But if these within the bracket, if it is equal to 0, then at that condition only your T should be independent of AF. Got it? So if this within the bracket is equal to 0, then only what happen? The whole second term will vanish, right? And then what happen? Your T should not depend on this AF. That is the meaning. So T should not depend upon AF. This is possible only if this within the bracket is equal to 0. That means sine I minus sine R is equal to 0. That means, this means what? Sine I must be equal to, if you transfer this to the right hand side, then sine I must be equal to what? Sine R. So these are both trigonometric functions. Okay, trigonometric functions or ratio, you can say. Sine same. So what happen? Your angle of incidence will be equal to angle of reflection. That is the first law. Now whatever we are considering here, it is nothing but this is all the cross section. Okay, so what happened? Your angle, your incident ray, the reflected ray, and the normal at the point of incidence, all these are lying in the same plane of the paper or your screen. Okay, so what happened? These three lie at the same plane, on the same plane, incident ray, reflected ray, and the normal lie in the same plane and at the same point, what is known as point of incidence. So this proves what? The second law of reflection. Now likewise, let's try to prove the laws of refraction by using what? Your Hudson's principle. Similarly, as we have done in the case of that of reflection, let's take it that this is the interface. XY is the interface between the two media. One is rarer medium here. Okay, let's take it that refractive index is having mu1, and the denser one is what? Having refractive index mu2. And the velocity of light in the rarer medium, as we have taken as air, so let's take it as velocity of light in the air medium as c, and that in the rarer medium, let's take it as small v. Okay. Now what happened when light ray travel from rarer medium to denser medium? We know that it bends toward the normal, right? So the angle between the incident ray and the normal at the point of incidence, it is denoted by angle I, and the angle between the refracted ray and the normal at the point of incidence, that angle we call it, these angles, as angle of refraction. This will be also angle of refraction, this will be also angle of refraction, and this will be angle of incidence, and that will be angle of incidence. As we have done in the case of that of reflection, what happened? This angle will be equal to angle of incidence. Similarly, this angle will be also angle of refraction. Now why this will be angle of refraction? Because this angle R plus 2, this angle, you take it this as angle 2. So angle 2 plus R will be 90 degree. Why? Because this will be the refracted plane wavefront, and this will be the ray. Okay, wavefront and the ray will be always perpendicular to each other. So R plus, let's take it this angle as 2, will be also 90 degree. So 2 plus R will be also 90 degree, because this is a normal at the point of incidence. Got it? So likewise, what happened? Your angle of refraction, this will be also angle of refraction, right? So now during the time, what happened? B reaches C. Okay, at that same time, what happened? This A also reach this point D. Okay, then what happened? Your CD will be the plane refracted wavefront. Now your BC and AD will be different. The distance will be different. Why? Unlike that of the reflection, that incident ray as well as the reflected ray, in the case of reflection it was air, but here in this, incident ray is in the rarer medium, but the refracted ray is in the denser medium. In the rarer medium, what happened? Light should travel faster. In this denser medium, light should travel what? Slow. Got it? So what happened? Distance traveled by the light in the denser medium will be less than that of the distance traveled by the light in the rarer medium, right? So your AD will be less than that of this BC. Now let's try to prove it that in order to prove that this CD is a refracted plane wavefront, what happened? We need to take it any arbitrary point from this incident wavefront, and we need to prove that during the same time that B reaches C, at that time E should also reach a particular point on the refracted plane wavefront. Okay, so from E it should reach G through this F, okay, at the same time, right? So let's try to prove it, that one. So let's take it that as we did in the case of reflection, T will be equal to what? The time taken by the light waves from B to reach C. During that same time, what happened? The light from E should also reach this point G. So what happened? This time will be equal to time taken by E to travel in the rarer medium plus the time taken to travel in the denser medium. That means time taken by EF to move EF plus the time taken by light to move this EG. Got it? So we know that distance travel by the body will be equal to what? Speed into time. So time will be what? Distance divided by its speed. So distance is EF and its velocity or speed in a particular direction is what? C. And for this FG, distance is FG and the speed will be what? V. So distance divided by V will be what? The time taken to move from F to Z, right? So those time, okay, the sum of the time will give you the total time to reach from E to Z, right? Similarly, like that as we did in the case of reflection, you try to express this in terms of AF, okay, by using your sign of angle of incidence, which is equal to what? Your EF divided by AF, and instead of EF you write it as AF sign. Likewise, instead of this FG you try to express in terms of FC sin R. Got it? By using your sign of angle of incidence R, angle of refraction R. Got it? From this right triangle FGC, if you try to find out sin R, then it will be equal to what? It will be equal to FG divided by what? FC. So sin R FC will be equal to what? FG. So by using that one, you try to express it in this way. And we know that FC is equal to what? AC minus what? AF, right? If you express it in that way, then you can express it in terms of what? AF here. Now, as I said, now if you take it for different points, okay, if different points onto this AB, suppose if you take your E somewhere here, then F will be somewhere here. Got it? So this time taken by the light rays from any point onto this, from any point from this AB to reach to the point on CD, it should be independent of this distance AF. Got it? It should be independent of this AF. So if it is going to independent of this AF, that means it should not depend on AF. That means within this bracket it must be what? 0. Only when this within the bracket is 0, then only what happen? Your time is independent of this AF. Okay, time, what time? Time taken by the light wave to travel this part. Okay, the time taken to travel this part should be independent of this AF. So that is what? Only when this within the bracket is equal to 0 means what? You equate it with 0, and then if you transfer it to this to the right side, then it will be sin I divided by C will be equal to what? Sin R by V. So if you cross multiply it, then sin I by sin R, this will be equal to what? C by V. This is nothing but this is your Snell's law. Okay, the ratio of the velocity of light in the first medium to the velocity of light in the second medium, this ratio bears what? A constant. Okay, and that constant ratio we call it as what? Refractive index of second medium with respect to the first medium, which is nothing but this is your first law of refraction of light. Okay, and as I said in the case of laws of reflection also, these are all cross sections. The incident ray, the normal, the refracted ray, these are drawn along what? In the cross section. That means they are lying on the same plane of your screen or paper, And so what happened, that proves what, the second law of refraction, that incident ray, refracted ray, and the normal at the point of incidence all lie in the same plane and meet at the point of incidence. That is nothing but that is the second law of refraction of light. Got it? Now let's see some behavior of a plane wavefront in a concave mirror, convex mirror, convex lens, concave lens, and prism. Okay, here I will not show you the prism. Prism will be shown in the next slide. Okay, now let's see how this wavefront changes from one nature to the another nature when it is reflected, when it is being refracted. Okay, let's see. In the case of reflection from a concave mirror, see the incident ray, okay, it is all parallel ray of light coming here. So parallel ray, that means it will be incident plane wavefront. So when it incident, it comes with the incident plane wavefront, but when it is reflected back, it is going with reflected back with spherical wavefront. How it is so? Let's see. Now incident wavefront, it is plane, so it will be vibrating in the same plane. So it will be in same phase of vibration. So if you join it all those same phase of vibration, then it will be a plane. Okay, now let's take it somewhere here. This will be also plane, but see these 2 points, okay, as soon as it incident on it, it will start reflecting. But when it reaches, see this point, when it reflects, okay, let's take it as small time, say let's take it as small t. During that time, the incident, okay, wavefront, okay, from this wavefront, it reaches this point. During that same time, this distance will be also there, the reflected wavefront. But for this point, okay, at this time it will not be reflected back, rather it will be reaching this point only. Okay, this point. So what happened when it reaches somewhere here, when this point reaches this point, when from this point it reaches this point will not be reaching the same point somewhere here, rather it will be taking only this much distance, for example. Then if you join it, then what happened, it will be what, not a plane, rather it will be a spherical one. Got it? So likewise, what happened, as I said, the distance moved will be same. Why? Because it is in the air. Okay, let's take it that these 3 points. Okay, first of all, let's take it these 3 points. Let's take it this as 1, 2, and 3 here, like this. So when this, okay, this point 1 moves this much distance, the same distance will be moved by this point 3 also. But this much distance will not be moved by the second point. Why? Because when this is starting reflecting this much, this light ray will only reach this point. Got it? So what happened when it moves back, that means when this light is reflected back, what happened, it will not move with the same distance, rather it will be short by this much distance here also. Got it? So when this one, okay, this point 1 reflected back and reaches this point, 3 will also take the same distance, but these 2 will be taking only this much point. So what happened, these are vibrating with the same phase of oscillation or vibration, so this will be having curve like this, not the plane one. So this will be what, concave spherical surface will be there, and we call it this as what, converging wavefront. Okay, converging wavefront. So from plane wavefront it is turning to what, spherical wavefront of converging nature. But in the case of these convex mirror, see the light ray, when it incident on it, what happened, it comes with the plane wavefront. Now what happened in this case, if you take it these 3 points here, okay, when these, okay, 1, 2, 3, when these 2, the light ray 2, okay, incident on it, it will start reflecting. but these 1 and 3, they are not yet starting its reflection. It need to move some more distance, right? Some more distance to get that reflected light. So what happen when these two, okay, light ray reaches this much distance, the light ray from 1 and 2 must be short of this much distance. So if it is like this, the planned wavefront, then that much distance will be also here. This much distance will be lagging behind by these two rays, 1 and 3. Okay, so it will be short of this much distance, and when this light ray from the 2, okay, reaches this point, what happen? This light ray will only reach up to this point. It will not reach this point. Okay, so what happened when this light ray, okay, from here it reaches here, from this light ray it will come back and it will only reach this point. It will go like this and it will come back and it will reach only this much. So these points are having what? Same phase of vibration. So when you join it all those points, then it will be what? Spherical wavefront. Now after reflection, what happen? It becomes what? Spherical. And this type of spherical wavefront is what? This is what? Diverging wavefront. Even though it is spherical, it is not always converging, rather it will be what? Diverging. In the case of this concave mirror, it was converging. Got it? And here it will be keep on diverging like this. Got it? So that is how it is done in this case. Now let's see for that of the light rays when these light rays pass through the convex lens. Now at this point here also, see, if you take it this as an incident wavefront, plane wavefront I mean, here the light need to travel a longer distance. Okay, the light need to travel a longer distance in this part. Okay, being this is a denser medium, the lens being denser, what happened? This light ray should travel a longer, it will take longer time I mean. But here in these two peripheries, okay, being thinner here, the light need to travel, okay, that what? Smaller distance of this denser medium here. Got it? So what happened? The peripheral rays will have to take what? Less time to emerge out of this denser medium. Got it? It need to travel what? It will take longer time to travel, but here it will take faster for these peripheral rays. Got it? So these, okay, when you compare the path length here with this middle one, okay, the path length will be more with the peripheral one than that of the middle one. Got it? So these will be all having the same phase of vibration. When you join it, it will be what? Spherical. And this is also what? Converging wavefront. Got it? Spherical converging wavefront will be emerging out. Okay, same is the case in the case of what? That of your concave lens. In the case of concave lens, what happened? This middle is of having what? Thin denser medium than that at the peripheral rays. These are thicker. Okay, thicker part need to be traveled by the light rays in these peripheral regions. So what happened? This will the middle ray will have to take longer distance than that of this peripheral. So this peripheral will take a shorter distance, but they are vibrating in the same phase. So when you join it, then it will be having that wavefront. What type of wavefront? Spherical wavefront. And this will be of diverging wavefront, spherical wavefront. Got it? Now that is also same in the case of what? Of the light refraction through this prism also. Now if you take it that the incident wavefront, okay, is a plane one, and if it is incident on it, then what happens? See, let's take it this as ray 1, 2 and 3 like this. This ray 1 will have to travel what? More thicker distance in the denser medium than that of 2 and 3. Okay, So the path traveled by the light ray will be more in the case of the ray 3 than that of 2 and 1. 2 will be the least distance and more will be what in the case of ray 2 and the longest in the case of ray 3. So when it emerges out, then what happens, they will be vibrating in the same phase. And so when you join it, all those points having the same phase of vibration, then you will get it as what? The plane refracted wavefront. This is the emergent wavefront actually, rather in the case of prism. So what happens when it is allowed to incident the plane wavefront, it emerges out as a plane wavefront. Okay, that is how it is happening in the case of what? The refraction of light through prism. So AB is your incident wavefront and we call it this as refracted wavefront. Rather, this is an emergent wavefront. Okay, you can call it either refracted wavefront or emergent wavefront, doesn't matter. Now let's take it up about the coherent source. What is meant by coherent source? Why we are taking this coherent source? Because coherent source is, to know coherent source is essential, because we need to learn this coherent source in the case of interference. The interference to take place, what happen, we require coherent source. So we need to know what is meant by coherent source. Coherent sources of light are those sources of light which emit light waves of same wavelength, same frequency and in same phase. Okay, if it is not having that same phase, it should either have small phase difference or constant phase difference. Okay, so that type of sources which emits out light waves, okay, of same wavelength, same frequency and same phase, we call it that as coherent sources. If they are not having same phase, if the phase difference between the two sources, okay, remains constant, then we call it that as constant phase difference. If they are having constant phase difference, then we can also call them as coherent sources, but this phase difference should be small. Okay, now coherent sources can be produced by two methods. The first one is what? By division of wavefront. Okay, that means from Fresnel's biprism or Lyot's mirror. That will not be discussed in this. Okay, I will tell you later on, okay, if you require it. So by division of amplitude, that means partial reflection or refraction. Okay, this will be done. I think it will not be included in your syllabus. Okay, that Bristol's law and all. So if it is included, then it can be considered there also. But we will not done this one. Just you know the method that can be producing this coherent source. You know that any two source of light, they are not coherent. They are not always coherent. Okay, but coherent sources can be obtained from a single source by means of these different methods. Okay, if the light is coming from a single source and if it can divide into two sources, then the two sources must be having the same phase, or if it is not having same phase, the phase difference will be always constant. That is the meaning. Okay, so those constant phase difference can be also called as coherent source, right? So that phase difference, constant phase difference or phase difference equal to 0 can be obtained from a single source only. So that process of producing two coherent sources from a single source can be obtained by these two methods. Okay,